Okay, welcome to today's lesson on complex numbers. Today we're going to look at a different form of a complex number. The form we've previously seen was called rectangular form. Well, today we're going to learn about a new form called polar form. And the way a polar form works is very closely related to the graph of a complex number, as we've seen in our previous lesson. So let me just quickly explain how this works. Let's suppose you've got a graph like so, and let's suppose that your complex number, when graphed, looks like this. Well, the length of your complex number, that's what they're calling r in your diagram. Let's suppose that was 5 units long. All right, so let's just suppose that the length of that complex number, the vector, is 5. Now the angle that we're going to be looking at is right here. These angles are always angles drawn in standard position, meaning that the initial arm is pointing along the positive x-axis, just like you learned in Math 1700. And the terminal arm is free to rotate clockwise or counterclockwise, although we want our angles to be positive, so we're only going to consider a counterclockwise direction. Let's suppose that angle there was something like 40 degrees. Okay? Then this complex number, if you were to write it in polar form, the shorthand notation would basically look like this. 5, which is the length of the vector, and then there's an angle symbol, because you have to write the angle in standard position after that, and the angle is actually 40 degrees. So this number here, that vector, would be represented by 5, your angle symbol, 40 degrees, and that's the number in polar form. That's actually the short version of the polar form. Okay, let's look at the diagram they give us right here. You can see your r is the length of your vector. How is that related to the a and the b, I wonder, of the number in rectangular form? J, that should be. How is it related to the a and the b? Well, here's your a on the bottom axis. Here is your b, that's the vertical length. And of course, here's your point a comma b. The real axis is, again, the horizontal axis, and the imaginary axis is your vertical axis. Well, if you look carefully at that diagram, and if we use a little bit of trigonometry, you can clearly see that a over r, if you remember this is a right triangle now, a over r is actually the cosine of angle theta. So a over r is equal to the cosine of that angle theta. And if you just multiply both sides of that equation by r, you end up with this right here. A is equal to r times the cosine of theta. Now, likewise, b, which is the opposite to theta, the opposite over the hypotenuse, so b over r, that is actually the sine of angle theta. And again, multiplying both sides of that equation by r gives us the second equation that you're going to require right there. So b is equal to r times the sine of theta. So basically, that's what you can replace the a with, and that's what you can replace the b with. And that gives you your polar form as well, a longer version of the polar form. How would you calculate the length of r if you knew what a was and if you knew what b was? Well, again, by looking at your triangle, you can clearly see it's just an application of the Pythagorean theorem. R squared is equal to a squared plus b squared. Think of r as being the hypotenuse of your right triangle. If you get the r by itself, by the way, here's the calculation that you would do to find r. It's the square root of a squared plus b squared. And that's the version of the formula that we're going to use. R, remember, is always going to be positive, always. But the a can be negative and or the b can be negative. And another thing that we can do to actually calculate the angle theta, given a and b, is, well, if you look carefully, b is the opposite side, a is the adjacent side, so b over a would equal the tangent of angle theta. So to calculate your theta, the reference angle now, theta would equal the inverse tangent of b over a. Now, one thing that's important to remember, when you do this calculation, when you calculate your angle, the first angle you're actually going to calculate is the reference angle, similar to what you did in Math 1700. So if a or b is negative, drop the negative signs. And depending on which quadrant your number ends up in, you may have to add or subtract it to 180 or subtract it from 360. All right, so we're going to do some examples of this here right now. Okay, here again is another way that you can see the angle written in polar form. I'll just underline it right there. This is the longer version. Okay, r cosine theta plus r sine theta times j. Notice that that's your imaginary part. Or if you take out r as a common factor, you could even see it written like this form right there. But more commonly, the way you would see it is r, angle symbol, theta. In other words, you don't even really see the j, but the j is implied. The j is there. R is always positive. All right, we have to have that. If your angles are not exact, and in many cases they will not be exact, round them to 1 decimal place. And we always want the angles expressed as positive values between 0 and 360. Actually, this second inequality symbol right there, that should be strictly less than. Because if you do end up with a 360-degree angle for your theta, you should call that 0. Okay? So let's look at some examples right here. Example number 7 on the bottom of page 13. Okay, what they want us to do there is take these numbers, and all of these numbers you will notice, even if they don't look like a complex number, they are complex numbers. They are all in rectangular form. So let's look at the first one. It's just 8. Now you can think of that as 8 plus 0j, if you like. And actually, we don't even need the calculation for r or for theta for this example, because this is a very simple example. All you need to do is think about if you were going to graph that number 8 plus 0j, where would it end up to? Well, there's a real part of 8, and there's an imaginary part of 0j. Well, if you graph that, ladies and gentlemen, that number will be pointing directly along the positive x-axis, just like that. There's your vector. And the length of that vector, again, no calculation required. You know that's going to be 8 because it reaches all the way to 8 on the real axis. The angle formed in standard position is 0 degrees. In other words, the initial arm and the terminal arm are pointing exactly in the same direction. So if you wanted to, you could write this as 8 angle symbol, because that's your r. That's the length of that vector, and the angle is 0, so you could write 0 degrees like so. If you wanted to write it in longer form, you could. This would be 8 times the cosine of 0 degrees plus 8 times the sine of 0 degrees multiplied by j. So there's the number. Both of those things mean the same. They're both polar form, okay? Now, b, 3j. Again, this is a simple example. Think of this as 0 plus 3j if you like. And now, if you were to graph that on a set of axes, where would the vector be located? Well, 0 for the real part means you do not go left or right, but 3j means we actually go up 3 units. So there's 3 on the imaginary axis. So the length of that vector is 3. The length of the vector is 3. So if that's your r, 3 goes in front, angle symbol. And now remember, the angle formed is in standard position. There's your angle right there. From the positive x-axis, or in our case, from the positive real axis, up to that vector is exactly 90 degrees. So again, for part A and part B, there were really no calculations required, because we can clearly see what r is, and we can clearly see what the angle theta is. Now, what about for part C? How is that one going to be any different? Well, it is going to be different because now the angle is not going to lie on one of the axes. Let me just erase this here to make some room for myself. Okay. So let's try part C. And this one's going to require actual calculations. Now, first of all, if you did graph this, 3 subtract 2j, 3 along the positive x, but then down 2, your vector is going to end up looking something like that right there. So it's going to be down in quadrant number 4 this time. When you calculate your angle, the reference angle is actually down below. But the theta starts from the real axis and goes all the way around in a counterclockwise direction, just like you were doing for Math 1700 in your last semester. So let's calculate our R. R is equal to the square root of a squared plus b squared. Now remember, use brackets for these. So your a is 3, so that's 3 squared. Your b is -2, that gets squared. Now remember, use brackets. That -2, all of it is squared, so that will become +4. So actually, you get the square root of 13. Now that's the exact value of R. You can actually use that if you wanted to, but if you use your calculator and find out approximately what that is, you get about 3.61. Now, the reference angle. Let's do that calculation. Like I said, in Math 1700, you were calling that alpha. You can still call it alpha if you like. It's equal to the inverse tangent, the inverse tan. Now, b over a, in our case, let me come down here, b over a is actually going to be -2/3, but drop the negative. Just go +2/3, because you want that reference angle to be between 0 and 90. So if you type this into your calculator, you're going to get approximately 33.7 degrees. But remember, that's not necessarily your theta. In fact, this angle right here, there's your 33.7 degrees. And if you want to get your theta, you would have to subtract that from 360. So theta is actually equal to 360 in this case. 360 minus 33.7 degrees. Why can't I get the degree symbol to come up? And you're going to get 326.33 degrees. Okay, so that number in standard position, everyone, or sorry, that number in polar form, you could write it as 3.61 angle symbol, 326.3 degrees. There's your angle. That's a degree symbol. Or if you wanted to, you could even leave it exact. You could just say root. Now, why can't I do that? Okay, I see what's going on. You could call that root 13 in front, and then 326.3 degrees. All right, so you could do it either way. I can't get my degree symbol. Oh, there it is. So I'll leave the other ones for you to try on page 14. Note very carefully, it's very important to determine which quadrant those angles end up in, those numbers end up in. And that's how you determine your theta. And very quickly on page 15, here's another example. Now these numbers are already in polar form. How do we change them back into rectangular form? How do we do that? Well, again, it depends on these equations. A is equal to R times the cosine of theta, and B is equal to R multiplied by the sine of theta. Now those are the two equations that we saw back at the beginning of this lesson. Well, there's your R right there for the first one is 5. You'll notice that the angle in both situations has to be the same, and that's your theta. So all you need to do is to calculate this one is A is equal to 5.00 times the cosine of theta. And that will leave us with, let me quickly get you the answer, approximately 2.94. And B is going to be equal to 5.00 times the sine of theta. And you work that out, and you will get approximately 4.05. So there's your A, and there's your B. So this number here, written in rectangular form, is actually 2.94 positive plus 4.05, and don't forget your J. All right, don't forget to write your J. And that's how you write from polar form back into rectangular. So I'll leave the other example for you to try, as well as the examples on page 15, and there's one on the top of page 16. And we're out of time, and I will finish this lesson. See you in the next one. Bye-bye.